Thanks. Right, so this is the time of day that jet lag sets in, so both for the speaker and the audience. Let me continue. So the first lecture was supposed to be an introduction, and I think more or less everything I said in the first lecture should have been rigorously correct. Now we're going to start doing some real problems where there are no mathematical results, we just have to see what happens. Okay. So let me go back to this Borel summation story and talk a little bit about quantum mechanics. Let's think of this cubic oscillator problem, which is a potential like that. So we know from the beginning that if we start trying to calculate low-lying energy states, that we expect them to be metastable. So we expect there to be an imaginary part, which we expect to be exponentially small. Okay? So if we just didn't know that, and we just did perturbation theory about that well there, then perturbation theory, because of the symmetry of the perturbation, will give you a series in lambda squared. Okay? And the even powers of the perturbation will survive in perturbation theory. And when that number is positive, lambda being real, we expect there to be some exponential stuff associated with the metastability. So if we think of the energy as a function of the parameter lambda squared in the complex plane, we don't expect it to be analytic, but we might expect there to be a cut along the positive real axis, just for the reason I just said. So let's just assume that that's the only non-analyticity. Then, if you want to calculate the energy at some point in the coupling plane, we could deform it by Cauchy, except we have to go around this cut. And now, what's the advantage of that? We've got energy as some function of some coupling, but now if we write it as a Cauchy integral, the coupling is no longer the argument of the energy. It's now here. So if we just assume that we can forget about things at infinity and there are no other singularities, we can turn this integral into an integral just along the cut of the imaginary part of the energy. Okay? And now we can expand in Z0, which is just going to recover the perturbative expansion. So in other words, the coefficients of the perturbative expansion are given by these integrals. Okay? Assuming there's nothing else other than this cut. So for consistency, we can now just argue from WKB, it's very easy to estimate the form of the imaginary part. Just by scaling, you can easily see that it's exponential of some constant, which you have to do some integral to work out the constant, but some constant over z. And if you do a little bit more work, you see there's a square root in front. And now, in order to look at the large order behavior of these coefficients, we want n to be large, it's dominated by z small, and then we can just do this integral, assuming this form of the imaginary part, and we get a factorial divergence. Okay? So this is an argument from Arkady Weinstein's very first paper when he was a student, which unfortunately wasn't published until about 10 years ago. And this captures a lot of the physics of what's going on here. So another version came from Carl Bender in his PhD thesis, was studying the quartic anharmonic oscillator. If you just do perturbation theory now, you get a series in powers of lambda, not lambda squared, lambda, the perturbation's even now. But perturbation theory doesn't really care whether lambda is positive or negative. You're just calculating the coefficients. It couldn't care less whether lambda is positive or negative. But clearly, if you change lambda from positive to negative, you see that in this case, we would expect unstable states with an imaginary part. Okay? So this is an argument that the perturbation series should be divergent. Because if it were convergent and you changed lambda to minus lambda, then you wouldn't generate this imaginary part. Okay? So Arkady summed it up nicely that one part of the story, it's not the only part of the story, but one part of the story is if at some phase of the coupling constant, maybe not the phase you were looking at, but at some phase of the coupling constant there's an instability, then you would expect perturbation theory to be divergent. Okay? So that's one thing. Now let's see what might happen in practice. I did an example last time where the coefficients were just n factorial. But let's generalize that to be something like this. Some factorial with a coefficient gamma, some shift delta, and maybe some power here. And this is the generic behavior of coefficients in perturbation theory. So now we can just reprocess the same way. We write the integral representation of the gamma function, insert it in here, do some juggling of coefficients, and you get this Borel representation here. So before there wasn't this power 1 over gamma because I took that to be 1, and there wasn't this factor of delta out here because I took that to be just 1, and beta wasn't there either, okay? And now you see that if I did this for a non-alternating series, I would generate an exponential that has a prefactor that depended on delta, and the power of the coupling in the exponent is no longer 1, it's 1 over gamma. Okay? In other words, if you simply know some information about the large order growth of the perturbative coefficients, you can learn what power of the coupling appears in non-perturbative terms. From knowledge of beta, you can work out the coefficient in the exponent, and knowledge of delta and the other guys will tell you the prefactor of the non-perturbative terms. Okay? So just from basic large order behavior of perturbation theory, you already learn some information about the non-perturbative contributions, okay, in the theory. Everyone see that? It's really a very simple argument, just scaling. So now let's go back and look at some of these examples that I showed you before and distinguish between the cases stable and unstable. You'll notice that in the Zeeman effect it's alternating, in the Stark effect it's not. Quartic oscillator it's alternating, cubic oscillator it's not. And the periodic potential in the double well, they're factorial but non-alternating. So what does this mean? Well, the Zeeman effect is clearly stable. You apply a magnetic field, you just shift energy levels. But if you apply an electric field, you shift energy levels and you have ionization. Okay? So you can derive ionization rates from perturbation theory by studying the rate of growth, non-alternating rate of growth of perturbation theory. It's not the most efficient way to calculate ionization rates, but it is a way to calculate ionization rates. Similarly, the difference between the quartic and the cubic oscillator is this is stable when the coefficient is positive. This one is unstable when the coefficient is positive. What about these two? These are the problematic ones. Both of these systems you expect to be stable, and yet the coefficients are growing factorially and non-alternating. So that's the puzzle. What's going on? So now let's just increase our level of sophistication a little bit. Let's look at these two cases. Now we all know here that there's a splitting of these low-lying levels due to tunneling, due to instantons, and in the periodic potential, these levels become continuous bands. We also know that the level splitting in both cases is a one-instanton effect by calculating the action of the instanton going from neighboring wells. You can calculate the exponent. Okay? This is chapter 1 in any book on this stuff. Okay? What's less well known is what happens if you go to the next order, or if you do perturbation theory. Let's imagine doing perturbation theory about these wells. I just told you on the last slide that it's divergent, and it's factorially divergent and non-alternating. If you look a little bit more closely, let's look at the coefficient. It's n factorial, but it's divided by the power of twice the instanton action. Okay? Now remember what I said on the last, two back. Knowing this coefficient here tells you the coefficient up in the exponent. So the fact that this perturbation theory had a 1 over 2s to the power n tells you that the corresponding exponential is e to the minus 2s over g squared, not e to the minus s over g squared. Okay? So the divergence of perturbation theory is not related to one instanton physics, it's related to two instanton physics. Okay? The other thing to note is that it's n factorial. It's not one of the wells.
Okay.
Okay. This is quantum mechanics. Yeah. But same argument for field theory. Yeah. Yep. I'll show you an example later. Okay. So this is a problem because taken at face value, this means that perturbation theory produces an imaginary part. These systems are stable. Calculating the energy here shouldn't produce any imaginary part. Okay? Moreover, it's ambiguous. We don't know what to do about this. In the other cases, the ionization cases, we knew what to do about the plus or minus because we knew it was decaying. So there was causality to tell you which sign to choose. And it's a two-instanton effect. Okay? So this was the puzzle that was resolved beautifully in work back in the late 70s and around 1980 by various people. Bogomolny, Zinn-Justin, Parisi, Brezin, etc., etc. Some very beautiful papers. And they realized that there was a problem in the instanton gas picture when you go to two-instanton level. So one instanton tells you the splitting, no problem, it's real, unambiguous. But at two-instanton level, you have to deal with instanton-instanton, anti-instanton, anti-instanton, and instanton-anti-instanton. And that last one, instanton-anti-instanton, attract one another. So it's an instability in the instanton gas picture, which assumes fast-separated dilute gas. So in order to regulate that problem, Bogomolny and Zinn-Justin proposed an idea of analytically continuing in the coupling so that they didn't actually attract one another. Okay? Then do the calculation, and then analytically continue back to G squared real and positive. Okay? Reasonable thing to do. And the amazing thing is that when you do that, you discover, under this analytic continuation, when you go back again, you generate an imaginary part, which is exponentially small. You can calculate it. And with a particular sign prescription, they noticed that it exactly canceled the imaginary part coming from Borel summation of perturbation theory. Okay? So this is the first view in our sort of physics of resurgence. There's a problem in the perturbative direction of this trans-series, which is there's an imaginary part which is exponentially small, which shouldn't be there. And on the other axis, the non-perturbative axis, once you go to two-instanton level, there's also an imaginary part, and they exactly cancel one another. Okay? So this is the tip of the iceberg of this whole structure of resurgence, that this should happen to all orders in the instanton expansion. Okay? So that in the end, the expression for the energy, which mixes now perturbative and non-perturbative contributions, is completely real, completely unambiguous to whatever order you stopped at in the. Okay? So that's the picture. Now I want to put flesh on that picture, but this was the first observation that something like this could happen. So let's just go through it a little bit more detail. Let's do this double well case. The coefficients with my normalizations here grow like 3 to the n factorial. Do your Borel, and you deduce an imaginary part for the ground state energy that goes like this. The 1/3. Okay? Now, so remember that 3 came from this 3 to the n here, which is just a fact of perturbation theory with this normalization. Now you do your instanton gas analysis, you find that it's very easy to calculate the instanton for this potential. The instanton action is 1/6 g squared. So the instanton gas picture, the splitting is e to the minus 1/6 g squared, but the imaginary part was e to the minus twice that. Two instanton effect. And now let's see how the cancellation works. Remember this picture of a trans-series that we have the perturbative direction, the non-perturbative direction, and the quasi-zero mode direction. We'll see this at higher order in a second. And the point is that these coefficients are quantitatively related. So let's look again. So let's just do the perturbative direction. So 0 instanton and therefore no quasi-zero modes. So these coefficients are growing like, in this case it was 3, 2s was 1/3, and alpha was some overall constant, and n factorial. So this gave this with a factor of alpha. So 2s here is this one-third. Now, this is some two-instanton effect. So let's look in the two-instanton sector. And let's look at the lowest order perturbative contribution in the two-instanton sector. And in the two-instanton sector, we want to have Q equals 1. Q can be 0 or 1 when K equals 2. And when Q is equal to 0, there is no logarithm. But when Q equals 1, there is a logarithm. And that logarithm produces an I pi because of that minus sign there. That minus is really e to the plus or minus I pi if I write it more carefully. But there's an I pi buried here when Q equals 1. Okay? So remember, this had an overall coefficient. This produces an I pi. So the coefficient with 0, 2, 1 better be minus alpha in order to those two to cancel. And you just go and do your calculation, and lo and behold, that coefficient is equal to minus alpha. Okay? It's equal to the leading coefficient of the large order growth of the perturbative sector, which you thought had nothing to do with the two-instanton sector. Okay? Independent calculations, and you just discover they're the same number. And now you can push it further. Let's push it further. Let's look at the one-instanton contribution. So there's this power 1. It's multiplied by a series. So there's e to the minus s over g squared. There's some series multiplying it. You can calculate these coefficients. That's not easy, but you can do it. And you could look at the large order growth of those coefficients. And you discover now that those coefficients grow like this. There's a new thing happens. Those coefficients grow like n factorial divided by 2s to the n. That's the same as the perturbative coefficients around the zero-instanton sector. But there's a log n factor with some coefficient, which you calculate from the large order growth of these coefficients. And there's a piece without log n. These are the leading two contributions. Okay? So that's simply a fact about perturbation theory in the one-instanton sector. You process that through the Borel machinery, and you see that that generates an imaginary part, which is e to the minus 3s. It's e to the minus 3s because there was already an e to the minus s, but you generated an extra e to the minus 2s because of this 2s to the n there. The log n produces a log g squared, and with these coefficients a and b. Okay? And that's just from doing those Borel integrals, nothing more. So this is a problem, but because of the 3 there, we know that that should be cancelled by something coming from the 3-instanton sector. So now we go to the 3-instanton sector. So now K is 3, so Q can be 0, 1, or 2. So when you do your 3-instanton sector calculation, you discover at the 0 perturbative level, the leading coefficient has a log g squared, a log g, and a c. It's really log minus 1 over g squared, the minus there. So you see, this term is really log of 1 of g squared plus I pi, or minus I pi. So you square it, there's a cross term, which is I pi times log g squared. This term just produces an I pi. Okay? So the imaginary part that you generate from here, these coefficients better match so that the cancellation occurs. And again, these are independent calculations. This is a calculation in the 3-instanton sector at 0 perturbative level. This was a calculation of 1-instanton sector, large order growth of fluctuations. Okay? You did those calculations separately. And you discover that these numbers are the same. Okay? Etc. You can now follow this procedure through the entire trans-series, and any imaginary part that you generate from perturbation theory will be cancelled by an imaginary part coming from some higher order in the instanton gas picture. In that way, this trans-series encodes all these interrelations, and the only way it can work is that these coefficients here these coefficients here have to be correlated. And they have to be correlated, with the right magnitudes, the right signs, everything. It has to work, otherwise there will be some leftover imaginary part that can't be cancelled by the higher stuff. It has to cancel order by order. Okay? You can grade this by the exponentials. And amazingly, you can do these calculations, these heroic calculations done by Zinn-Justin and company, and it really works. Okay? So later I'll explain to you why it works, but the starting fact is that it does work. Okay? And the idea of resurgence is that this should happen to all orders, yeah.
So the statement is that in the cubic oscillator, the imaginary parts won't cancel out.
Yeah. We know why.
Okay.
Usually people obtain that one instant or one anti-instant is the exact solution, exact classical solution. But multi-instant case is connecting a one instant solution. Yeah, it's not the exact classical solution, I think.
No, this is an instant-on gas calculation. Okay? Far separated.
That is a gas picture.
Yeah.
This,
I'll tell you how to do it properly later. I'm telling you. Okay. This is the instant-on gas picture of how to derive a trans-series. It's very convincing that something like this is underlying it. Okay, so let's think of upgrading to quantum field theory. So let's go through a few arguments. There's this extremely beautiful paper by Dyson, 2-page long paper with one equation in it, which is this equation. It's often quoted as a proof of the divergence of QED perturbation theory. It's not a proof. It doesn't pretend to be a proof. He explicitly says it's not a proof, but people think it's a proof. And the argument is extremely beautiful. Imagine you calculate G minus 2. It's going to be some series in alpha, right? That's all there is. So alpha is just E squared to us. And his argument was, suppose this was convergent. That means with some non-zero radius of convergence. That means that within that radius of convergence, everything's smooth and analytic and nothing funny is happening, and you can freely analytically continue E squared. But then Dyson said, but that can't be right, because there's a huge physical difference between E squared positive and E squared negative. In one case, we're trying to build a QED vacuum where electrons repel, and in the other case where they attract. That's the argument. Therefore, for that physical reason, this thing should not be convergent. Okay? Extremely beautiful, probably correct. The proof of this has defied some of the real heroes of quantum field theory to come anywhere near a proof of this. The divergence of perturbation theory is proven. It was proven before this for scalar field theories by Hurst and then by Tiering. But as soon as you go to QED, nobody understands how to control the cancellation problem between fermion loops and boson loops. So it's not enough just to bound and count diagrams. There are all these cancellations. Okay, so that's the homework exercise for any students here. There's a very explicit example of this from Heisenberg and his student Euler, which is really the beginning of effective field theory. He calculated the one-loop QED effective action. So here's just Maxwell, then at fourth order, you have this term, et cetera, et cetera. When the background field is constant field strength, you can actually do this calculation in closed form. And this effective action encodes the nonlinear properties of the QED vacuum, and similar argument for QCD. And in fact, Heisenberg's paper, Heisenberg and Euler's paper, it's not clear to me how they got this formula in the abstract, but somehow. This is the Borel transform of the answer. It's a Borel integral, and this is the Borel transform. This is the exact non-perturbative answer. If you want to expand it in the background field, you'll get this, diagrammatics. But why bother? Because you have the exact answer. Okay? But if you expand it, so this is specialized now to just one background field, just a constant magnetic field. This is that integral. It's a little simpler if there's just a magnetic field, not an electric field also. The coefficients are known. They're just Bernoulli numbers. So they grow like 2n factorial and alternate in sign. Okay? Moreover, they go like 2n factorial, but it's b squared. That's the parameter. So remember my argument that the rate of growth and the power up in the exponent, so the fact that it's 2n factorial tells you the exponent thing in the exponent will be the square root of the expansion parameter. The expansion parameter is b squared, so it's b again, okay, or 1 over b. So you can look at the growth of these Bernoulli numbers. The Bernoulli numbers can just be rewritten as a factorial times a zeta function, which is just a sum over these. And you can now go through the exercise. If you're interested in learning about this stuff, this is a very beautiful exercise. You can do it, you can do everything. And you can reconstruct the Borel transform. So this thing here is just this sum over k with these poles, and the poles are coming from this rate of growth, but the location of the poles shifts because of this k. So the poles are at plus or minus ik over ik pi. Okay? And now you can ask, well, what happens? The B field is the analog of the Zeeman effect. You're applying a magnetic field to the vacuum, like applying a magnetic field to an atom, and you just get a real shift in the vacuum energy. But if you apply an electric field to the QED vacuum, you get a shift in the vacuum energy, but you also get ionization, which means pair production. And you can calculate the imaginary part of the effective action just by doing this Borel business. And it's a sum over instantons, e to the minus k, and the basic instanton factor just came from this, with b replaced by e, and the factor of pi coming from here, pi k from here. That's where that sum came from. Okay? And so this so-called Schwinger effect, where you get pair production from vacuum subject to an electric field, you can also solve this problem using perturbation theory processed through Borel summation to get the right imaginary part, which tells you the rate of decay of the QED vacuum. Okay? So this is a beautiful example of extending that argument from quantum mechanics to field theory. It's also an illustration of Dyson's argument, because changing B's magnetic field to an electric field is replacing B squared by minus E squared, because the invariant is B squared minus E squared. Okay? So it's just flipping the sign, but under flipping the sign, it's clearly unstable because you're applying an electric field. So therefore, the B field case couldn't have been convergent because you need to produce this imaginary part. Okay? So that's the sort of argument we'd like to be able to construct in field theory. And you might think, okay, well, this is pretty simple because this, in the end, is just quantum mechanics of particles tunneling out of the Dirac sea. But this exact same problem shows up in many cases. If I did it not for a background magnetic field or an electric field, but a background self-dual field, which means that the external photons have fixed helicity, then the expression is this. Instead of cosh here, coth here, it's 1 over sinh squared. If you do the Gaussian matrix model, it's exactly the same expression. C equals 1 string, it's exactly the same expression, just rotated by pi over 2. And you do the Chern-Simons matrix model, it's exactly the same expression, just summed over various topological sectors. Okay? So this is not an empty example when you think of applying these ideas to field theory. And in all of these cases, you can just use this Borel structure, and those exponential terms that you generate are parts of the trans-series. In the language of mathematical trans-series, they're a little bit boring because they're not multiplied by fluctuation factors. And that's because these things are just meromorphic functions. There are no branch cuts anywhere here in this Borel transform. Okay? And this sort of pattern shows up in a lot of these localizable theories. They're basically integrals like this. They have poles, and you can do all this Borel stuff, and you can find the saddle points, etc. But they're a little bit oversimplified because they don't have these fluctuations very often, because often the Borel transforms are just meromorphic functions. Okay, there's another example in de Sitter space, which I don't think I'll go into, but the difference between de Sitter and anti-de Sitter is you change the sign of the curvature. So at the formal level of a formal series, it's just turning one from alternating to non-alternate. And then there's an interesting fact that there's only pair production in de Sitter space, not in anti-de Sitter space. And it's even more interesting because in de Sitter space, it's only even-dimensional de Sitter space that has pair production. And you see that only in even dimensions is it actually asymptotic. In odd dimensions, actually convergent. So that's another interesting example. But let's get to something a little bit more sophisticated and think about asymptotically free quantum field theories. So in quantum mechanics, in those examples I just described, the core reason for the rate of divergence of perturbation theory is just combinatorics. The number of diagrams is just growing factorially fast. That's a quantitative statement. The number of diagrams has been classified in all sorts of field theories. You can look up the papers, and it's just factorial growth of the number of diagrams. But in an asymptotically free theory, the coupling will now be running, and there are new effects associated with renormallons due to the momentum dependence of certain diagrams, and there are certain classes of diagrams that produce a rate of divergence in perturbation theory that turns out actually to be faster. So it's still n factorial divided by twice the instanton action to the n, but it's multiplied by the leading beta function coefficient to the power n. And that number typically scales with n for your sigma model or gauge theory, okay? So beta 0 is bigger than 1. And if you want to do large n, it's much bigger than 1. So this, I'll just rewrite it like this. So what this tells you is, first of all, there are plus or minuses. That's associated, remember, the ones that are non-alternating are the ones that produce these imaginary contributions. The ones that are alternating just produce real contributions through Borel summation. And in these asymptotically free theories, it's the infrared limit that produces the non-alternating one, and the UV limit that produces the alternating guys. Okay, so what this means is that from perturbation theory, you generate exponentials with an imaginary part, which involve 2s, but 2s divided by beta 0. Whereas the instantons that you know and love in these very same theories, the instanton-anti-instanton interaction will generate I with e to the minus 2s over g squared, with no beta 0 there. Okay? So this is the infrared renormallon puzzle. It's very beautifully described in some of Tufts' Ereche lectures. So what it means in the Borel plane, there are these poles associated with the UV renormallons. They're on the negative t axis, so they don't cause any problems with inducing imaginary parts. But there are poles on the positive axis that will produce these imaginary parts, and the imaginary parts will be like this. And remember, there's a correlation between that factor and the location of these poles, by that argument I gave before. Okay? Whereas the instanton and anti-instantons give you a pole at a location further from the axis, which means that the exponential contribution is actually smaller. Okay? So the dominant problematic guys are not the instantons. Instantons are actually somewhat irrelevant to this discussion. The dominant ones are caused by these infrared renormallons. And the fact that these exponents are different means that they can't be cancelled from one another. Okay? All right, so this is a problem. It was well known, it was well ignored. And then we came back to it some years ago now. There's another problem with the instanton gas. It's not just a problem that instanton and anti-instantons attract. That's the instability that you want to regulate. There's another problem, that in these asymptotically free theories, the instantons are scale invariant. So there's an infrared divergence with integrating over the scale invariance. So that has to be regulated somehow. And an obvious way to do it is some sort of compactification of the manifold that puts a cutoff on the size of the instantons. And in this couple of papers with Mittard Unsal, we use this spatial compactification with twisted boundary conditions that I'll describe on the next transparency in the CPN model, and actually showed that in that case, the basic non-perturbative objects actually sit on exactly the same location as the infrared renormallon poles, and you can also calculate the prefactor, and the prefactors agree also. So let's see roughly what's happening. So instead of considering the CPN model on the plane, let's consider it on a cylinder. We'll take it to be a spatial cylinder with Zn boundary conditions around the spatial circle. There's a reason for that. With this Zn twist, actually these instantons fractionalize, and they fractionalize by a factor of 1/n. So this is a 2D version of Van Baal's sort of construction in the 4D Yang-Mills. And this 1/n is interesting because beta 0 in the CPN-1 model is just n. Okay? So here's a picture. Here's on a large radius cylinder. You make it smaller and smaller, and this blob fractionalizes into things that are just localized around here, and it fractionalizes into 3 pieces. This was CP2. So what that means is now, on this cylinder, you go to an asymptotically free regime where you can do a weak coupling analysis, which means small radius of the cylinder. You now do an instanton gas calculation, but with the basic dominant semi-classical objects, which are now these fractionalized instantons. Now you can do that calculation, and this is what you get. The instanton-anti-instanton interaction has some real part, but it has an imaginary part, which is ambiguous depending on how you regulated this instanton-anti-instanton interaction, and you can calculate the exponent and you can calculate the prefactor using standard instanton gas pictures, but using your basic instanton constituents as the fractionalized ones, because they're the leading objects, because of the 1/n in the exponent. And then you compare it with the perturbative sector calculation, which you can simplify here, because in this is why these 2D models are simpler. In this small radius limit, it actually just reduces to quantum mechanics. So you can do a calculation using quantum mechanics, do the Borel transform, you generate an imaginary part, and you see that these things just match exactly. Okay? The first test is that the 1/n turns up here, and the second test is that the prefactor matches. Okay? So this is an exact example of this BZJ, Bogomolny Zinn-Justin quantum mechanical style cancellation at the first order at which it should happen, which is at the 2-instanton level. And presumably, we would hope that something like this continues through higher orders in the instanton gas picture.
It's a finite n state?
Yeah, there's no need for large n here. Okay, so that's interesting, but now we should look at some other sigma. That was CPN, which has, in many ways, some common features with Yang-Mills theory. It has instantons, it has theta parameter, etc. But there are other sigma models that have the very same problem in perturbation theory, but they have no instantons. So, for example, the ON model in 2D, the O3 model is just CP1, it has instantons, but when n is bigger than 3, there are no instantons. Okay? There's no instanton equation even. The principal chiral model has no instantons. Okay? But they have this problem in perturbation theory. So what am I talking about? What's interesting about these models, they don't have instantons, but they have finite action, quantized action, solutions to the second order equations of motion. Right? Remember, instantons are factorized equations of motion, first order equations. They automatically satisfy the second order equations, and you have this sort of theta parameter structure of the solutions. These models, remarkably, have topology, but for a different reason. They have solutions to the second order equations that are perfectly regular, finite action, quantized action, but they're not solutions to any first order equations, but they are exact solutions to the second order equations. So physicists knew this for many years, and mathematicians, but they didn't know what these solutions meant, because these solutions have unstable fluctuation directions. Instantons are stable. You look at fluctuations around instantons and everything's fine. Okay? All the directions are stable. These solutions, however, the fluctuations have negative directions, and so people just sort of ignored them, said they're unstable, so we don't need to worry about them. But actually, that's a good thing. They have unstable directions, so the fluctuations around them can produce imaginary prefactors. Okay? So in fact, you can now do the same sort of analysis in these theories, using now these fractionalized saddles. They're not instantons, but they're saddles. And these guys play the same role as the instanton-anti-instanton interaction in the CPN model. Okay? And match with the Borel analysis of the perturbation theory. So that's good, because otherwise I could have just stopped right now. So this is happening in other interesting theories. But I want to stress, and this is not widely known, it seems, that the CPN model has instantons, but it also has exact instanton-anti-instanton solutions. And they're classified. Okay? There's an algorithm to generate all instanton-anti-instanton, all non-BPS solutions in the CPN model. Right? Even on a cylinder, even with twisted boundary conditions. So what do they mean? Why are they there? They're not minima of the Euclidean action, but they're saddle points. Well, if we're going to talk about calculating path integrals via saddle point analysis, I have to tell you what happens at every saddle point, why some saddle points might contribute or not to certain quantities and at certain phases. Okay? And you see that in these cases, here, it really is these saddle points that are repairing the ambiguities and imaginary contributions coming from perturbation theory. What's not widely known is that Yang-Mills theory also has exact non-BPS solutions. So a simple example, take SU4. So take a 4x4 matrix representation and take it as two 2x2 blocks with zeros on the off diagonals. Okay? Put an SU2 instanton in the first 2x2 block and put an SU2 anti-instanton in the second 2x2 block. Okay? This lives in SU4. It's obviously a solution to the second order equations, and it's obviously not a solution to the instanton equations. Okay? The action is 1 minus 1, it's 0. Okay? It's an exact saddle in SU4. What's really non-trivial is that these also exist in SU3 and SU2. And for that, I'm going to have to, there are papers by various mathematicians showing that. Okay? It's not understood yet what they mean, because while we understand just about everything about fluctuations around instantons, almost nothing is known about fluctuations around non-BPS solutions. But I want to stress that these things should be understood for this whole proceeding.
Are there other solutions known beyond these embeddings?
Yeah, so in SU2, of course, you can't play that game that I just said. So that's the non-trivial work of Karen Uhlenbeck, to show that there are solutions even in SU2. Constructing them is more difficult. In SU3, there are some actual Ansätze that you can write down, and you find the solution up to numerically integrating some radial functions. Okay? SU2, it's a much more abstract analysis, and I think that's why the fluctuation problem hasn't been studied. But I just want to bring to people's attention that these are out there, and they should be understood for this story. So the resolution that we're proposing based on these 2D models is that these guys have unstable contributions, fluctuations, or can have unstable fluctuations, which can play the role of instanton-anti-instanton molecules in the theories with instantons. Okay. So
just so there was these additional things they came up with a beta naught in the where the instanton action is there. Is there an understanding of why that is the case with these non-BPS saddles?
Oh, with the non-BPS. So in the examples, yes. In general, no.
Okay, but somehow it just works out.
In the 2D examples, we understand, but in 4D, we don't know.
But
even with the instanton-anti-instantons, it doesn't match, right? Because the fractionalization is 1 over n, but beta 0 is not n.
Okay. But in this particular non-BPS saddles where you do know it matches, you have an understanding of beta 0.
I can show you.
Okay.
All right, so those are just some examples. As I said, this is now experimental physics and experimental mathematics. We're working through examples to see what happens. Hopefully, at least you get some feeling that some of these cancellations, some of this resurgent structure relating fluctuations around one non-perturbative sector and another one should happen and must happen, and there's some evidence that it's happening in field theory. But I want to step back and ask, why is it happening?
Can I ask another question? So this renomenon in the Yang-Mills theory, so is it understood what happens if you Higgs the theory? Is it also because there's a conformal invariance and so on, which you break? If you Higgs the theory, something nice happens? Or?
Yeah, it's much simpler. There are papers on that I can read. So I want to ask, what's going on? Why is this happening? We've got evidence that it's happening, but forget about perturbation theory for a second. Just think in terms of path integrals and see, why is this working? So there's this beautiful quote from Hadamard that the shortest path between truths in the real domain passes through the complex domain. So that's going to be my motto. I want to tell you something about steepest descents that's not very well known. And it actually came as a byproduct of some work by Michael Berry and Chris Howells. They were studying something called hyperasymptotics, which we don't really need to know about. But in the process, they looked at the following problem. Just take an ordinary integral with some function here that has multiple saddle points. And multiple can mean 2 or 3 or whatever, it doesn't matter. And there's some large parameter here, 1 over g squared. And this is supposed to be the integral through one of the saddle points of that function along the steepest descent contour. Okay? So this integral is perfectly well defined. Okay? I can calculate that. And for each saddle point, I'll have such an integral. Because for each saddle point, there's a unique steepest descent contour through that saddle point. So the usual approximation we then make is we have the leading factor as the exponential, just the function evaluated at the saddle point. And then there's some Gaussian fluctuation from the vicinity of the saddle point. That gives you some prefactor. But there's also a series. The rest, the cubic, quartic, etc., produces a series in g squared, which we usually neglect and forget about. Okay, so I want to tell you something interesting about that series. So let's expand it in powers of g squared. So there are going to be some indices here. So remember, n labels the particular saddle point, and the subscript r is going to be the order of the perturbation around that saddle point. Okay? Now, with relatively mild, actually amazingly mild conditions on the form of this function f, you can now just do contour deformations around just taking these steepest descent contours and wrapping them around one another. And you can show this exact formula, that this series around saddle point number n is actually given by a sum over all the neighboring saddle points, and I have to tell you what neighboring means in a second, of some integral transform of the fluctuations around the other saddles. So here, the picture is, there's some contour through this guy, there's another one here, there's another one here, and I'm calculating all orders of the fluctuations around there, and I can wrap these contours around the other ones, and there's sum over the other ones, there's a -1 depending which way they wrap, which way the contours go, and there's some exact transform of the fluctuations around the other ones, where capital FNM is the difference between the function at the different saddle points. So it's like the action difference between these saddle points. So that's a rescaling of this transform. But now you see that g squared appears here, not here. This is like that dispersion relation argument I gave before. So I can just expand this. And now you see that will give me an expansion in g squared of this guy in terms of this guy. So what you learn is that the large order growth, remember notation, these are the coefficients of the fluctuations around this saddle point. At large order, meaning large value of little r here, It's factorial. And then the leading coefficient is the difference of the saddles from here to here to the power r. That's like the action to the power r. It's the action difference. And the overall coefficient is just the 0th order coefficient from this guy. And then the subleading is not r minus 1 factorial, it's r minus 2 factorial. And that coefficient is the 1st order of the fluctuation around this guy. And then the sub-subleading is the next fluctuation around this guy. And this is exact. Okay? So I strongly recommend you can go back to the airy function example. Airy function, there were 2 saddles. Very simple example. You can calculate the fluctuations around them in known functions. They were just those hypergeometric functions. And this is the explanation of why the large order growth about one of the saddles was related to the low order growth around the other saddles. It wasn't something special about the airy function. It's something about contour integrals. It should be in every physics book, but it isn't. Okay? When you go beyond this Gaussian approximation, there's structure there. Right?
So what is FNM exactly?
Sorry?
What is FNM?
It's the difference. So that's the action evaluated n. That's the, so F and M is the difference. Action difference. So it's as if you got products of the contributions, or ratios, I guess. Okay, so there's this explicit relation between the saddles. So let's do an example. Let's do a 0-dimensional path integral with sine squared. This integral, well, it's just a Bessel function. It's an integral representation of a Bessel function, but it has 2 saddle points at 0 and pi over 2. And this one's really a minimum, this one's a saddle. And since you can do everything, the coefficients are just these. You can expand them at large r, and then you can go look at the fluctuation around the other saddle, and they're just the same coefficients. Okay? This is large order growth around saddle 0. This is low order terms around saddle 1. You can repeat that exercise for any special function you like. You just look it up in some table of integrals book and check that this behavior is completely generic. Now you can go do it for a function that doesn't just have 2 saddle points, that has 3. And again, you now find that the fluctuations around this one feel the fluctuations from the other 2. That this one feels the other 2, and this one feels the other 2. So there are explicit, very strong quantitative relations between the expansion coefficients. Okay, so this had nothing to do with perturbation theory. But if I did this problem a la the problem from the airy function from this morning, we would have learned this fact from studying the large order of the fluctuation. This is the explanation in path integral language of why it's happening. Okay? But you notice that in order to explain it in path integral language, I had to do deformation of contours. Okay? It was the key step. So now we can be very ambitious and say, this is the explanation of why there are these relations between fluctuations around different non-perturbative sectors. Could something like this work in the infinite dimensional case of a path integral? So there's a lot of literature here, and even going from 1 dimension to 2 dimensions is already interesting. And there's a vast literature on this multidimensional exponential integrals. It's called Picard-Lefschetz theory. So we want to somehow be very ambitious and go directly to infinite dimensions, bypass 2, 3, 4. So of course, there's nothing to look up. You just have to do a calculation. So now, instead of doing this 0-dimensional partition function, let's just do quantum mechanics with this potential. Okay? So you can just do a calculation. Remember, I told you that the coefficients grow like n factorial, but you can calculate the subleading corrections. Right? It's a calculation that's not too hard. Then you can do a fluctuation calculation around the instanton anti-instanton sector. That's not so easy. But after doing a lot of hard work, you learn that these coefficients are those coefficients. Okay? So this calculation is almost trivial. This is very complicated. And now you go do the double well again. And now there are these funny coefficients here with this factor of the action squared, etc. And then you go do a instant on ant, instant on saddle calculation, and you see the same bizarre numbers showing up. Okay? So the moral here is that something's going on, that we don't really understand how to do it in standard, conventional, Feynman diagrammatic sense, but something's really happening. And it looks exactly like this Berry-Howell's argument from deforming contour integrals for ordinary exponential integrals, which is proven using contour deformation. So it very strongly suggests that there should be some definition out there somewhere of deforming the contours in a path integral. Okay? Follow the sort of semi-logic there. All right, so it encourages me at least that it's not a waste of time to look for these contour deformations. In fact, it's even more. How much? Only 14 minutes? Okay, all right. In fact, there's a lot more structure than this. It's much deeper. This was some generic large order, low order relation. There's actually much more explicit relation. So I'm going to have to maybe go through this a little more quickly. It's not so interesting how this is calculated. There's something called uniform WKB. It's just an easier, better way to do WKB calculations. You write the wave function not in standard WKB language, but you just admit that in these, for low-lying states in these harmonic vacua, the solution is approximately a harmonic oscillator. So why would you write it as an exponential? So you write it as a parabolic cylinder function, which is the solution to the harmonic oscillator of some function. And now when you do WKB, there's no problem with turning points. Everything's smooth. It's much simpler. Okay, so that's uniform WKB. You then just do perturbation theory, expanding in this function here. And you learn that the energy is a series in G squared with some coefficients, and the coefficients depend on this parameter that I introduced, which is going to turn out to be related to the level number of the harmonic oscillator in each well. Okay, but at this point, it's just an introduced parameter. If you set this parameter equal to n, you just get ordinary perturbation theory about level number n. Okay? This is not Borel summable, but it's pretty obvious why it's non-Borel summable, because I didn't tell you the full story. I just did perturbation theory about one of these wells. I didn't tell you about the other well. Now, in these cases, we can use parity here to say that the lowest state should be even and the next state should be odd. Likewise here, we can say that the state at the lower level of the band should be periodic and the state at the upper level of the band should be antiperiodic. That gives you a condition that this solution should either be zero or its derivative should be zero at the midpoint. Okay? So that's a global boundary condition that we didn't yet impose. Right? So because it's non-Borel summable, I have to take this coupling G, which actually tells me the location of the midpoint, and I have to continue it slightly off the real G squared axis, either up or down. But now you see that I have parabolic cylinder functions in the complex plane. So at large 1 over G, I need to look at the asymptotics of these guys not just on the real axis, but in the complex plane. So now you go look them up. And you see that there's an exponential guy, e to the minus argument squared with a series in 1 over z. But there's another piece which is e to the plus, which normally you don't care about because you choose nu to be an integer, which kills this guy. That's the quantization condition for a harmonic oscillator. But now we're in the complex plane, so we should keep both of them. But now I want to impose this condition that at the midpoint this thing's zero, or its derivative is zero. So that gives you a condition between this and this, evaluated at the midpoint. Okay? So I get some very non-trivial equation which says that e to the minus some coefficient over g squared, remember the location of the midpoint was 1 over g, is equal to some power of g coming from these prefactors that have to balance with some gamma function, and then there's some junk coming from the perturbations. which is I've collected here. And this is exact. Okay? So this determines nu, this parameter nu, as a function of g squared. And you see that if g is 0, then this is 0, so nu has to be an integer. That's when the wells are completely decoupled. So if g is not 0, but just very small, then this thing is very small, so nu has to be close to an integer. So you just look at this equation and you plug in nu equals an integer plus something, and you match terms. And you learn that this parameter psi is exactly this instanton factor. And so nu is an integer plus something small plus another term which is instanton squared. And you see this log just showed up. The log came from this fractional power of g squared here. And there are some prefactors, there are some factors here which are expressed in terms of this guy. And you clearly expand this as high order as you like. And now you see that nu is an integer plus something exponentially small, but also logarithms. So you just go back to this formal series expansion. Remember, these were polynomials in nu. Insert this, and now we have a trans-series. We have a series in g squared. Each order is multiplied by a polynomial in nu, and nu is a series in exponentials and logarithms. So this is where the trans-series came from, and the logarithms. This is the two-instanton sector. Instanton, anti-instanton interaction gave me this log. Okay? So now you can check, and this is a demonstration of this conjecture that Zinn-Justin and Genshura came up with from doing detailed multi-instanton calculations and numerical calculations. They proposed that the entire trans-series could be generated just from knowing the perturbative series and from knowing the fluctuations around the one-instanton sector. They argued that everything else would follow. And the argument is basically this. This is the fluctuation around one instanton, and all these higher ones are expressed in terms of the same function. Okay? So that shows where that came from. So the leading order is this, plus or minus one instanton times the fluctuation, and everything else is expressed in terms of this and this. So this is almost the resurgence picture. Right? This is the vacuum. Fluctuations around the vacuum, well, that's perturbation theory. One instanton sector, fluctuations around that is this. And all the other ones are determined in terms of that. Okay? So we're getting close. But it turns out it's much more interesting than that. It turns out that this function is expressed in terms of this function. There's an explicit relation that the fluctuations around the one instanton is exactly equal to this function, which is just generated from the derivative with respect to the level number of the perturbative sector. So remember, the derivative with respect to the level number is the density of states. Okay? So in other words, and remember, these were all generated from these two, so this means that everything in this trans-series is generated from this formal series. Okay? So this is amazing. This is, infinite number of instantons, because this is an infinite dimensional problem. And yet, computationally, you can check this to as high order as you wish. All of the data for the fluctuations around all of these instanton sectors can be written in a simple closed form, not large order, low order stuff, just a closed form in terms of this function. So in other words, that's my seminar next week. It's not so hard, it's all orders WKB. It's not so hard now that I understand it. So, what this means in practice, I want to stress, this is not this generic large order, low order relation that I argued before was always going to be true. This is much stronger. This says that if you'd give me 10 orders of this fluctuation, the 10 lowest orders, I can automatically write down the 10 lowest orders around the one instanton, and around the two instanton, and around the three instanton. Okay? Just the same numbers. If you try to do this the hard way, which in these heroic papers a couple of years ago by Shuriak and Turbiner and Escobar-Ruiz, they did it for this double well and the Sine-Gordon case. So diagrammatically, you have roughly 25 three-loop Feynman diagrams, and the propagators are propagators in the instanton background. You do this horrible calculation of adding up all these diagrams, some of which you have to calculate numerically. And they calculated this coefficient here. And with that relation on the previous slide, we can, and this was for the ground state, so n equals 0. So with that formula on the previous page, I think this is the double well. I honestly don't remember at this point which one. Yeah, double well. This is the expression for any n. You set n equals 0, you see the 71 over 72, and this number agrees with this to the stated decimal places. Okay? So clearly this is telling you something. That this way of doing it, this Feynman diagrammatic way of calculating the fluctuations around the one instanton sector, is monumentally inefficient. Okay? If I can simply write it down in one line, by assuming, or having proven this resurgent structure. Okay? So this is a challenging problem, and diagrammatically this is still completely mysterious. This is not understood why this complicated diagrammatic calculation gives the same answer. Okay.
So is there a statement about the partition function, like say thermal partition function? So this is a nth eigenstate.
Yeah.
So can one exponentiate it in some?
One could, I haven't, but let's talk about that. That's an interesting question, actually. Yeah. So at this point in a talk, there's usually somebody puts up their hand and said, this can't possibly work because in supersymmetry, perturbation theory is 0. So how can that encode these fluctuations around? So somebody asked that question, I'll give you the answer. Okay. So in a supersymmetric theory, the ground state energy perturbably is 0 to all orders. And yet I just told you that the perturbative sector can generate all the other sectors. So how does it work? Well, let's look at a case where we have broken supersymmetry, say the double well. And now, non-perturbatively, there is a contribution to the ground state energy. It's exponentially small. It has a fluctuation factor. This is the one instanton contribution. There's a fluctuation factor, and it's positive, obviously. You shift the energy up. Well, you can check that this fluctuation factor here is exactly given by this formula that I wrote down before. And you'll notice that this formula actually involves the density of states. It's the derivative of the energy with respect to the level number. So the point is, in these supersymmetric theories, the energy at n equals 0 is 0 to all orders, but the derivative with respect to n at n equals 0 is non-zero. Okay? So what I mean, more precisely, is knowing perturbation theory not just as a function of the coupling, but also as a function of the level number. That's what perturbation theory means. That information is enough to generate the fluctuations. Okay? You can test it in the periodic potential, where the ground state energy is still 0, supersymmetry is unbroken, and now you see that it's actually a contribution from two saddles that actually cancel one another. And exactly cancel one another, including these fluctuations. It's an extremely sophisticated cancellation between these. It follows from this, this relation, okay? So let me just recap. There's extremely strong evidence now that in these non-perturbative calculations in quantum mechanical models that we all use as toy models of instantons, but also in some two-dimensional sigma models, that there is this sort of generic resurgence cancellation, high order, low order. In other models, there's even stronger evidence that there's explicit relations between the fluctuations around the perturbative sector and any other non-perturbative sector. And these are quantitative relations. I mean, there's no discussion. They're simply true. The real challenge is to understand why they're true. And my proposal is that this can be understood through this thimble picture of deforming contours into the complex plane in a path integral in analogy to that result of Berry and Howells from ordinary contour integrals, which explained why these different saddle fluctuations were connected to one another. Okay, so I've run out of time, but let me just stop there. Thanks.
Gerald, questions? Yes.
Just to sort of flesh out my understanding a little bit more, if I go back to the cubic quantum mechanical oscillator, where you started off, there was this discussion in terms of it had to be a power series expansion in lambda squared. So if I take lambda to be I lambda, so the theory is PT symmetric, then of course you know, or you believe that there is no imaginary part, right? The energy levels are real. And I can understand that because I'm generating an oscillating series at that point, and that's the way to think about it. So it's perfectly Borel summable. And
So Carl Bender and I wrote a paper on this many, many years ago, showing that that argument, that Borel summation when the coefficient is I times a real number, matches with his results from PT.
So that's another way of understanding how it all fits together.
The cubic oscillator,
More questions? Yeah.
Maybe I should have heard this with my jet lag. I didn't hear it. When you go to the field theory case, you have, of course, an infinite dimensional integral, but your contour is always taking the entire field through the complex plane together, right? Is that the idea? So there's really you're only thinking about one complex variable which you uniformly change all of the real fields to the complex plane?
No, hold on.
I mean, if I were to put this on a lattice, I would have n integrals, right? And I could imagine different contours for each term on the lattice. But this is a single contour.
Contour is no, sorry.
So I'm asking what you mean by the contour change. You have a field
So
theory.
that's why one dimension is a little bit deceptive, because you can trade a rotation of phase of the large parameter for a rotation of the variable.
Right, so I want to go to the field theory, yeah.
So now we go to the field theory. It's really deformation of the field variable integrals. So step one, complexify the field variable. Step two, find the steepest descent contours in that field space. They're still one-dimensional, right? They haven't doubled the degrees of freedom.
Right, it's still a single complex variable for the field uniformly at all points. Yeah. And that's clear, that's all you have to do.
Right, so remember, a steepest descent contour is one for which the imaginary part of the thing in the exponent is constant. That's the definition of a steepest descent contour by, whatever it is, Cauchy-Riemann. Okay? So that's good, because it means, if we're going to think about, it's sort of good, because if we're going to think about Monte Carlo, it means that along such a contour, the imaginary part's fixed, so you can take it out. I'm trying to give you sort of motivating examples that it's worth taking this seriously. So that's the idea. And we'll hear some talks later this week of actual implementations.
Just naively, if these fluctuations around the points are related, shouldn't there be also like a symmetry in field space to relate this? Then?
Why?
I mean, or...
So the example I gave, it was simplified by the fact that it was a symmetric one, but the argument that was just to simplify the analysis. I mean, there's something called Darboux theorem from calculus, which is that the fluctuations around some point, right, when you do real analysis, it's very difficult to calculate rates of convergence of a series. But as soon as you go into the complex plane, it becomes very simple. because you just look for the nearest singularity and the distance to the nearest singularity. So this is a generalization of that idea. You've got some special points, the fluctuations around the point, their rate of growth is governed by the nearest singularities, which are the nearest other saddle points. That's basically it. And that doesn't assume any symmetry.
There's this whole program being pushed by NEMA saying that Feynman diagrams are a terrible way of understanding a theory. Is there a connection between what they're talking about and the similar looking statements you're coming up with saying that Feynman diagrams completely miss the global picture?
So, yes, but not yet in a very useful, I'm very pragmatic. I don't think there's a constructive way of implementing that, but that's clearly part of the motivation here. There's a lot of evidence that Feynman diagrams are incredibly inefficient at high orders. So one step in that direction is you can convert to this sort of world-line formalism, which already makes a big improvement to standard perturbation theory at high orders. And that has a much more natural interpretation in this language. Once you rephrase perturbation theory in terms of world lines, because you can think of saddle points now in that expansion. But that's not the whole, there's more than that. Because I'm thinking about systems where there are these saddle points. And the other description could apply in just general theories without saddle points, without instantons, without topological solutions, classical solutions.